So in 5.2, we'll be looking at the first law of thermodynamics, which is all about this concept of internal energy. And what internal energy is the sum of all the kinetic and potential energy of the system. It's just basically summing up all the energy. And these two scenarios, these two pictures here, just really go through, what you already know, that if a system starts out with a high energy and then ends with a low energy, then energy must be lost to the surroundings. And if the system starts with low energy and ends in high energy, then it must have gained energy, and it gained energy from the surroundings. That every time that something gains energy, something else must lose energy. Energy is never created nor destroyed. This is just that same concept, except a specific example. The specific example here is with the combustion of hydrogen gas and oxygen gas to produce liquid water. This reaction is what we call exothermic, and you can see here that it starts out, the reactants have a higher amount of internal energy, mostly potential energy. And then as the reaction takes place, the products are more stable. They have less potential energy. So where did that energy go? The only place for that energy go is to be lost to the surroundings. This would be an exothermic reaction. So we've talked about exothermic and endothermic before. That's the same as always. What we're going to look now into a little bit is, when we say that it loses energy to the surroundings, it can lose energy. So the change in energy can be in two forms. It can lose energy by Q, which is heat, or W, which is work. Right? If you think about that, explosion or the reaction of hydrogen gas and oxygen gas making water, that's going to produce an awful lot of heat. But if that is contained in some way, it can also do some work. And so this table down here, table 5.1, just goes through some of the terminology that we use. And a positive Q means that the system gains energy, and a negative Q means, or heat, and a negative Q means the system loses heat. Pretty straightforward. It's a little bit sometimes trickier when we start talking about work. The positive energy, or positive positive work would mean that work was done on a system. And the negative W would mean work is done by the system. So if in the example from the first video where that reaction pushes up against the piston, that is the system doing work. That would mean that W is negative. And so there's lots of questions that really ask you to apply that concept. So here gases A and B are confined in a piston, cylinder and piston arrangement like in figure 5.4, react to form a solid product. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. The piston moves downward as the gas reacts to form a solid. As the volume of the gas decreases under constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. What is the change in internal energy? Right, so as always, right, think of the formula, then plug in our numbers, and then solve for the answer. So delta E equals Q plus W. Now I go through the problem and I look at what does this mean. So if it loses 1150 joules of heat to the surroundings, right, it loses. So that means that Q is going to be minus 1150 joules. Work is done on the system. So if work is done on the system, right, that's positive, right? Work done on system means that it would be a positive 480 joules. And then I sum those up, I get negative 670 joules. Simple as that. But that really means that you need to understand that table on the previous slide. Here is another practice exercise. Consider the following 4 cases, and then how many of these cases does the internal energy of the system decrease? So that really, what is that saying? That delta E would be a negative number. So chemical process in which heat is absorbed. Well, if heat is absorbed, right, that would mean that delta E would be a positive number. A change in which Q equals 30 and W equals 44, well, that would be 30 plus 44. That's also a positive number. A process in which a system does work on its surroundings with no change in Q. So does work on its surroundings means a negative W, no change in Q, so that would mean overall it would be decreased. So this one will work. So we have at least one. A process in which work is done on a system and equal amount of heat is withdrawn. So work is done on a system would be positive, heat is withdrawn is negative. So this one would have no change because it says an equal amount. So the answer there is just B. And practice exercise 2, here's another one if you want to pause and try this one on your own and then unpause the video so you can see your answer for yourself. It says calculate the change of internal energy for the process when the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. So remember formula. Delta E equals Q plus W. The Q here, it absorbs 140 joules, so that is positive. And it does 85 joules, so that's negative 85 joules. And that comes out to be positive 55 joules. Okay, we can then apply the terms endothermic and exothermic to these systems, which we've been doing for a few years in science, right? That if I look at this scenario right here, I notice that the temperature goes down. If the temperature goes down, then what has happened, this can be really tricky. If the temperature goes down, then what you are measuring is the surroundings. So if the surroundings lose energy, that must mean that the system gained energy. And that's why it's an endothermic reaction. It often, students want to think the opposite, that if it's an endothermic process, it will get hotter. But you need to remember that what you are measuring, you're not measuring the energy of the this, it doesn't say, but this kind of looks like a very common reaction where you mix ammonium chloride and barium hydroxide, I think. And you mix those two and it makes this solution and it absorbs energy. A lot of students want to say, well, if it absorbs energy, then wouldn't it be positive? But it's the actual atoms and molecules themselves that are gaining potential energy. Their bonds are changing. If they're gaining potential energy, they have to be gaining that from somewhere else. And what you're feeling is the surroundings. So that's why you see that the temperature goes down. If you get confused by that, the exothermic reaction is much more easy to understand. That if it is an exothermic reaction, the temp of the surroundings will go up. And so that's why explosions, we sort of know that combustion and explosions are exothermic. If we put our hands up to, we feel the heat that's being released by it. So the opposite must be true for an endothermic reaction. So if it feels hot, it's exothermic, and if it feels cold, it's endothermic. And this last piece here talks about state functions. Now, state functions are not something that you need to know for the AP exam, but it will help you to understand a little bit about Q and W. So a state function is If a measurement is a state function, that means that it depends only on the present state of the system and not the path the system took to reach it. Many of the things that we will look at are actually not state functions, that it just depends where they are right now, right? So if you look at this, I have 50 grams of water at 25 degrees Celsius. It is indistinguishable from, well, did it used to be 50 grams of ice that has melted, or did it used to be 50 grams of really hot water that has cooled? Once the system has reached that middle ground, you cannot tell it that how it got there is of no consequence. Internal energy is a state function. So that means, like we were saying before, it only depends on the initial and final states and not how that change occurred. Q and W are not state functions. That's why. Because they are not state functions, if one changes, the other will have to change so that delta E stays the same. That's weird. Let's look at this example here. So this is a fan that's running on a battery, right? And as the fan runs on the battery, it loses, the energy that's lost by the battery, the delta E, is a certain number. Some of that is lost in the form of work because of the rotor spinning around. So that must mean that another amount of energy to make that up must be lost in the form of heat. That's why when motors run, usually they feel hot, right? Your computer feels hot. The back of your television feels hot. Sometimes your phone may feel hot. Not so much with your phone. You can feel just the latent heat coming off of it. This is an example of maybe like a toaster where only the energy is lost only as heat because it does no work. So this is just that, the concept that energy is composed of those two, and if it's going to lose 100 joules of total energy, it must be made up in some version of work and heat, that those two things must come together.